solving first-degree inequalities in one unknown. Once you've cracked first-degree equations using the properties of equality, next is mastering inequalities in one unknown. In an inequality, the two sides of the expression are unequal. They don't add up to the same thing. In these examples, there is one unknown, x. Inequalities are all around us in real-life situations. Think about the driving age. To get your driving license, in many countries, you have to be 18 years old or older. If x is the legal driving age, then the inequality can be expressed. X is greater than or equal to 18. For safety reasons, some rides at the amusement park don't allow passengers under a certain height, like the roller coaster. You must be taller than 1.2 meters to ride. So, if x is the height allowed, the inequality, the unknown height, could be expressed as x is greater than or equal to 1.2 meters. Now imagine this. It's the annual school fair, and as one of the activities, Mona has been asked by Miss Dareen to sell at least 30 apples this week. Mona managed to sell a total of 22 apples in the first 4 days. How many must she sell on the last day of the week to succeed in her challenge? Let's express this as an inequality. Our unknown x is the number of apples that Mona needs to sell in order to succeed. She has already sold 22, so x plus 22 should be greater than or equal to 30. Her teacher said at least 30. That means she could sell more if possible. Let's try and solve the inequality. Like equations, we first isolate x. Inequalities, also similar to equations, have similar subtraction properties. So, to isolate x, we subtract 22 from both sides. The result is x is greater than or equal to 8. Mona needs to sell 8 or more apples to succeed in her challenge. Now let's take a look at Amgad. He managed to save more money than his sister Reem, and their dad gave them both 5 more pounds. Like equations, inequalities have similar addition properties. And so, Amgad will still have more money than Reem. This is called the addition property of inequalities. Whatever number you add to one of the sides of the inequality, you need to add to the other side. This applies to subtraction as well. Let's see how. Both Amgad and Reem have decided to buy a new coloring book for £10. They pay £5 each. Who would end up having more money left? It's Amgad, because he started with more money than Reem, and they both spent the same amount. This is how the subtraction property of inequalities works. Let's take a look at this. X plus 4 is less than 7, and we know that x is a natural number, so the answer cannot be a negative number. Then what would be the value of x? We know it can only have a value of between 0 and 3. To isolate x, we subtract the number 4 from both sides of the inequality. Then, solution set must be equal to the set containing 0, 1, and 2. We express this as x, such that x is smaller than 3. This could also be represented on the number line. Since the unknown x is less than 3, we count back to the left, starting from the largest number of the set, 2, and down to the smallest natural number, which is 0. Let's take a look at another property of inequalities. Suppose Sally has a bag of 3 oranges, while Hassan has a bag with 2. The inequality would read as 3 is greater than 2. Their teacher, Miss Nelly, teaches Sally and Hassan she will give each one the same number of oranges again. That means that however many each of them has will double. This could be shown as a multiplication by 2. The inequality remains true after multiplying both sides. Let's try another. How do we solve x in this equation? let's isolate x. How do we do that? Knowing the multiplication property of inequalities, we can multiply both sides of the inequality by 4. That would result in x being greater than 8. So, the solution set would be the set containing the elements 9, 10, 11, 12 onwards. This time, our solution set is an infinite set, looking like this, and expressed as x, such that x is greater than 8. But what if we multiply by a negative number? Does the multiplication property of inequalities still hold true? Let's take a look. X divided by minus 2 is less than or equal to 3. Now let's isolate x. We have to multiply both sides of the inequality by minus 2. But unlike when multiplying by positive numbers, as before, we have to reverse the inequality sign. The same rule applies to division. When dividing an inequality by a positive number, the inequality sign doesn't change. However, as in multiplication, when dividing by a negative number, we must change the direction of the inequality. But why does multiplying or dividing by a negative number reverse the inequality? Well, to explain this, let's take a look at the number line. For example, from 3 to 7 is an increase, right? But what about from minus 3 to minus 7? It's a decrease. That's why multiplying or dividing by negative numbers reverses the inequality. Sometimes inequalities require several operations to solve. Let's take a look at this example. Minus 2x plus 15 is greater than 3, and x is an element of n. To solve x, we need to isolate it. First, let's subtract 15 on both sides of the inequality. Next, we have to divide both sides by minus 2. And what do we do when dividing by minus 2? We reverse the inequality sign. This is expressed as x, such that x is less than 6. We know that x is an element of n. In that case, the solution set is the set that includes the numbers 5, 4, 3, 2, 1, and 0. Let's recap. Remember, when adding or subtracting a number to both sides of the inequality, the sign of the inequality stays the same. When a positive number is multiplied or divided by both sides, the sign also stays the same. But when we multiply or divide the sides by a negative number, we reverse the inequality sign.